Nobody knows how hard 3 set is, and nobody knows how hard independent set is. But we know their difficulties are related, and we can use cracking as a tool to relate those unknown difficulties. We can say, for example, that independent set is at least as hard as 3 set. So we're going to dig into the taxonomy that humans have come up to understand their own ignorance, something known as complexity classes, and we'll start with something known as the class P. So we'll say that a specific computational problem is in the complexity class P if, first, it's a decision problem, and second, you can solve it in big O of n to the k time. So what's a decision problem? Well, it's just any problem where you can say, is the answer, where the answer is yes or no. So for example, does there exist a pair of duplicates in an array? That's a yes-no question. Not a decision problem is how many duplicates. So it's a decision problem if the answer is yes or no. And in an example, we might have of a problem in P, we might say, are there 2 items in an array whose sum is 0? Well, here's one solution, the one we have from discussion. Take the array, sort it, and then once you've done that, walk pointers towards each other until you find something that they sum to 0 or they cross. And I'm not going to go into that now since it's from an old discussion worksheet, but the runtime of that algorithm is n log n for the sort, and then n for the pointer walk. And so the overall runtime is bound above by n squared, since n log n is less than n squared. So in that case, we can say that the answer to this problem of checking if 2 items in an array whose sum is 0, that is big O of n squared, so it is NP. So another class is known as NP. So NP is, yet again, decision problems, just as before. But now the difference is that instead of the problem being solvable in n to the k time, we just need a yes answer to be verifiable in big O of n to the k time. So more precisely, we want to, when we solve such a problem in NP, we get back a particular answer, and we want to make sure that we can verify the answer quickly. Okay? So as an example, is there an independent set of size k? Well, yes, you run an algorithm, it gives you back some red vertices q, and so to verify this, we check just all the vertices they said, these are the ones that should be red, and we make sure all their neighbors are white. That verification step takes qn time, which is big O of n squared. So that's an example of a problem which is, we don't know how to actually solve the independent set problem quickly, but we can certainly verify a yes answer very quickly. Okay? So an example of a problem that's not a problem in NP, even though it sounds kind of like one, is how big is the biggest independent set for graph G? And this is not one simply because it's not a yes-no problem. Okay. So if you want to distinguish between P and NP, you can think about it this way. These are the problems you can verify yes answers quickly. And so Clyde Kruskal, a mathematician, has suggested that VP would be a better name than NP, which would stand for verifiable in polynomial time. Okay. So why does this matter? Why are these classes useful? Well, I'll start with P. Problems in P are the problems that are regarded as easy. So theoreticians need some way to taxonomize problems. What we can say is that for typical n and k, a P problem can complete execution within at least a human lifetime. Now, of course, you can mess with the definition of the class P. You can say, oh, well, an algorithm that finds the median in n to the 50,000 time is not very good, and you'd be right. But it turns out that algorithms just practically don't look like this for whatever reason. Okay? And so we can say that for practical problems, the exponents are going to be small. They're not going to be n to the 50,000. And yeah, we really do need to worry about things like constant factors. But if we're just trying to, at first blush, establish in some broad sweeping way what problems are easy and which ones are hard, P is a great starting place. But, it is a little artificial. Because really what we care about is that we get results when we within hours or seconds or whatever for our particular application, but this is just a broad theoretical view to say what problems we consider easy, can be solved in n to the k time. Why does NP matter? Well, one reason is that most practical problems, or at least many, can be cast as something in NP. So if you're running an airline, you might ask the question, is there a way to route all of my airplanes, including all my staff and everything, where we should fuel up, where the repair should happen, at a total cost of less than $1 billion a year? And if the answer is yes, then our algorithm should give me a proof that I can then go and check everything, and if I have a nice financial model, it'll say, okay, everything's good. So it's verifiable quickly. Now, it could be incredibly hard, and nobody knows how to solve this routing problem. But given the appropriate financial models and a nicely written out specification, we can verify at least. We can check all the line items and say, great. Another is, well, is there a way to route the wires inside a microchip so that I have, all these little wires inside of this thing with a total path length of less than a micrometer? Again, it might be incredibly difficult to actually find the routing, but given a particular routing, if the answer is yes, it's possible, I can verify it by just tracing it. Another, well, given a number z, are there two primes out there such that x times y equals z? So if I can answer this question, if I have an algorithm that can answer this question and say yes, well, then if it gives me an answer back, x and y, then I can easily verify that the product is 0. I just multiply, which is going to be very quick. Okay? And so all of these problems, right, they give you a sense that NP problems are useful. You might think this one seems very silly, but this problem underlies a lot of modern encryption, makes commerce on the web possible. Okay? And I'll omit this one for now. Now you may say, what's so special about yes? Why don't we discuss problems for which a no answer is verifiable? There is actually another complexity class known as co-NP, which discusses such problems, but we're not going to say them today. Really what I want you to get out of this today is that there are some problems that are easy to solve and some problems that are easy to verify, and that the ones that are easy to verify are very practically useful. Okay, so this brings us back to independent set. So why is this useful? Okay, how does this connect to this whole complexity class framework? Okay. Well, how hard is independent set? It lives somewhere in between this gigantic gulf of space between linear and exponential. And what we can say is that the independent set problem is an NP, right? Tuisa is an NP problem. So the question we're basically asking, in some sense, what we want to know is, well, is this some incredibly difficult problem that's fundamentally exponential? Or is perhaps there some solution that is quick? Is independent set in the class P, the set of problems that are fast? And that's a great question. So this is where, oh boy, ready to layer yet more definitions on you. Rapid fire, all right? So I'm going to define a problem pi. It's a new problem, whatever, some problem pi. Pi could be 3 set, independent set, whatever. And I'll say that that problem pi is NP complete if 1, pi is a member of NP, it's part of the set, and 2, pi cracks every other problem in NP. Okay? Why would this be useful? We'll get there. But it raises a couple of interesting questions. Are there any NP complete problems? Do any exist? Is there any problem in the class of all verifiable yes answer problems that can be used to solve any such other problem? And do we know how to solve any of them efficiently? And this brings me to why it'd be useful. Suppose there existed an NP complete problem, right? We have some problem that can crack everything else. It's a universal skeleton key that unlocks every single verifiable problem in the universe. If we knew how to solve any of those efficiently, then we'd be able to solve all of those problems very efficiently. So it turned out that in 1971, Stephen Cook showed that the 3-SAT problem, the one we've discussed as NP complete, it is a master skeleton key. That if you could solve 3-SAT efficiently, you could solve literally any yes-no question for which you can verify things quickly with that problem. It's kind of a deep, crazy thing. That is, integer factorization, airline scheduling, wire routing inside of a microchip. 3-SAT solves it. Somehow there's some way to take any NP problem, literally any easily verifiable yes or no question, and it could be solved with 3-SAT. And that's pretty crazy. Okay. And so the punchline there is that if we could solve 3-SAT, we could solve any yes or no question whose answer we can efficiently verify. And again, 3-SAT was this right here. Okay. And so that was Cook. Levine later showed in 1873 a similar result. And if you want to know how it works, you can check it out there. But just to give you a very rough idea, you can imagine building a giant Boolean logic expression that represents the entire state of your computer at every time step. And if the solution to that takes polynomial time, then that means that we can build a Boolean logic circuit that's polynomial in size. And by Boolean logic circuit, I mean some kind of 3-SAT expression. And as an example of what the logic variables might represent, like x1, for example, it would represent true if the 57,173rd bit of memory is true, and we're on line 38 of code during cycle 7,591,872 of execution. Some kind of backbending contortions, though, to show that in principle, that you can build a 3-SAT circuit that will solve any problem out there, because you can basically encode the state of a computation over time. Okay. So in other words, 3-SAT solves any problem for which a yes answer can be efficiently verified. Okay? It solves independent set that we've talked about. It solves airplane routing. It solves the traveling salesperson problem, wire routing, the Hamiltonian path problem we haven't really discussed, 2' integer factorization, and Hamiltonian cycles. All of these things, because they're yes problems that can be verified quickly, they are cracked by 3SAT. Now, also of note, in 1972, our department's very own Dick Karp showed that 21 well-known NP problems crack 3SAT. So, for example, independent set can be solved to crack 3SAT. In fact, we actually did that earlier, right? We did the construction, very similar to Dick Karp's. And it turns out that traveling salesperson cracks 3SAT, and Hamiltonian path cracks 3SAT, and so forth. So therefore, it cracks every single other, so the Hamiltonian cycle, right, or the independent set problem, we'll stick with independent set. Since independent set cracks 3SAT, and 3SAT cracks everything else, then independent set is itself also a master skeleton key to everything. And since the time of Dick Karp's original 21 problems, there have been many thousands of additional problems that are NP complete. For example, finding the longest paths in a graph, finding the minimum number of edges that we can add to a graph so that it contains a Hamiltonian cycle, which is a cycle that visits every vertex once, determining whether or not a given made-up Super Mario Bros. Level has a solution. So in other words, if you can solve any of these problems, you can solve any efficiently verifiable problem. Okay? And so whenever you want to prove that X is NP complete, you simply have to crack any NP complete problem with X. So for every single one of these, now we basically have determined that there are like 2 or 3, 5, 10,000 master skeleton keys. And if you can show that any new problem can crack any of those problems, it also joins the club because 3SAT cracks them all, right? And so basically, as the number of NP complete problems continues to grow, it gets easier and easier to find new NP complete problems. And if you could solve any of them, you can solve all of them. Okay? That's the state of where we are here. So if we summarize and go back to 2ISA, right? What is the runtime of our independent set problem? Well, it turns out there's a lot more to this. We've opened up a giant, crazy universe. And we can say that the runtime of 2ISA, whatever it is, it's the same as thousands of other interesting NP complete problems. It's the same as 3SAT. It's the same as Super Mario Bros. Levels, finding the longest paths in a graph. And so basically, if someone could prove, for example, that they have to take at least exponential time, I write a proof that you cannot prove, or that you can't solve Mario Brothers in less than exponential time. That would apply to all of these problems, 2ISA, everything. And likewise, a proof about X, say at 2ISA, would apply to all other such problems. So what we've done is we've grouped everything in one giant class of problems, but the answer right now is we don't know. We don't know how hard it is. Okay? So far, to summarize, P are those problems that could be solved quickly. NP are those problems that could be verified quickly. And NP complete problems are NP problems that crack all other NP problems. So what we know, we can draw a Venn diagram, right? We have the space of NP problems, those that can be verified quickly. Among those, there are some that can actually be solved quickly, and naturally P is a subset of NP, because if you can solve something quickly, you can certainly verify it quickly. I mean, just solve it. And we have NP complete, which are the special NP problems for which having one solution to any of these solves all of these problems quickly. Okay? And so it's an open question whether or not any of these can be solved quickly. And one way that it's often stated is, are efficiently verifiable problems somehow also efficiently solvable problems? Because if any of these dominoes fall, the whole thing's easy. Okay? So we live in a world, possibly, where these two sets are actually the same, but we just don't know now. That is, we don't know if independent set is actually a hard problem that we can do no better than n squared times 2 to the n, or if maybe there's some trick.